All right, everyone, we're ready to begin. So now I'm going to pass it to Dr. Joris Wagners for an introduction, and then we'll begin the show.
Okay, thanks for coming. Good to see you all. To Seattle and the good rain. An hour, 15 minutes from Kenmore to here, just in traffic. Anyway, I want to take a couple of minutes here and tell you a little bit about this guy that you all know quite well, etc. But you may not know that Danny's actually a college dropout. So he's officially a college dropout. After high school, he attempted college, said, okay, bag this. After 2 semesters, volunteered for the Air Force and spent some time working on a B-52. So he and I actually did interact, although not in person or even virtually, because I was consulting on a B-52 at the same time that he was actually doing the hard lifting on it. So after 6 years on the flight line, he got admitted to the officer program and did his BS in EE next door here. And then he did operational test and project management work on the MQ-1 and the MQ-9 RPVs. So at that point, he then got selected for the doctoral program on the Air Force thing, very competitive. And so anyway, he showed up in my office upstairs, said, gee, I kind of like things that are going on in the autonomous flight systems lab. And I want to do I got admitted to the PhD program. I said, oh, okay, well, welcome. So it's been a real pleasure working with him. And he will be sorely missed because he was one of the bright lights, including a bunch of the folks here in my retirement of 22 years. So now I can officially retire, having handed the reins over to Karen, my colleague, who has been doing a remarkably good job. And she was a co-advisor with me on Danny's work and really a great benefit to the program and to what we did. So anyway, without further ado, Danny, lead us through your progress on research.
All right. Thank you for that introduction. And thank you all for being here today. It means a lot to me. And I'm really excited to share this dissertation work with you called Altitude Constrained Occlusion-Aware UAV Coverage Planning for Autonomous Search and Rescue. So UAVs have basically become a mainstay in the search and rescue community. They're used for a variety of reasons. And overall, they just make the search more efficient and safer for the operators. Even so, with all these advances in sensor technology and UAV capabilities, there's still these remaining challenges that kind of linger, and especially when we're talking about this scenario where you're using a small, maybe quadrotor backpackable UAV in a wilderness search and rescue setting. So during my time here at the University of Washington, I've been able to work with a lot of very talented folks on a variety of these problems that are all related under this umbrella of search and rescue in a wilderness setting. First of those was this challenge of doing object detection or detecting people from aerial perspective imagery. So as a lab, we published this large-scale hand-annotated data set that you can use to train computer vision models to automatically detect people in these type of settings, both in visual and thermal imagery. We also worked on the challenge of doing multimodal image fusion, where you're trying to create a fused image that represents the features from both visual and thermal in hopes that'll provide better object detection. Another big challenge is the ability to send your UAV beyond line of sight. So these wilderness terrains are really complicated. And so in this scene, like it may be very beneficial to go check out what's beyond the ridge in the background image there, but it might take you several hours to reach on foot. And so being able to send your UAV there would be very beneficial because you can make it there in minutes. And this isn't really a technology hurdle. This is more of a procedural and regulatory hurdle and also a financial hurdle for many SAR organizations that are comprised of all volunteer forces, and so often they're self-funded. And so we focused on doing a low-cost implementation of this beyond visual line of sight concept, and we'll be publishing on that later this year at SciTech. And then related to today's talk is this idea of perception-aware planning. And I had the distinct privilege of working with some brilliant people who are here in the audience today, Sam Buckner and Chris Hayner, from the autonomous controls lab on something that they worked on called adaptive deferred decision trajectory optimization, which allows us to do this kind of perception-aware planning loop. For instance, this project I'm showing you here is called HALO, stands for Hazard-Aware Landing Optimization, where we're trying to land a quad rotor on Mars and trying to sense data with a LiDAR and find these flat spots that are free of debris on the way down. And then today we'll be talking about this Occlusion-Aware Wilderness Search and Rescue mission, and that'll be a focus of today's discussion. We'll be publishing or submitting a journal article on that very shortly. So before we understand the problem that we're trying to solve, I want us to get all on the same page with how UAVs are used in these scenarios. And so if you're on the UAV team supporting a wilderness search and rescue mission, you're going to get a role or an area assigned to you by the central authority. This is an incident commander who's in charge of directing the search effort. And there's these two distinct roles. There's a UAV operator role, and then there's an imagery analyst role. And together as a team, you're supposed to provide visual evidence back to the incident commander that will inform the rest of the search and how it evolves. The important thing to note here is that visual evidence means we are trying to detect the person. That's the most critical task. We're looking for somebody who's lost or maybe injured and need help. But a very close second is the ability to rule out areas that you've already covered. That's a very valuable tool to have because it answers questions for the incident commander, like where should we search next? Or do I need to send a ground team to go do further investigation in this area? So this is really challenging, and it becomes even more challenging when you consider that many UAV operators wear both hats. So they have to do both of these tasks at the same time. And to hammer this point home, you all get 10 seconds to try to identify the human in this short 10-second video clip. So there's a human who's laying down and wearing a yellow reflective vest. So good luck. All right. So I want you to note just how much information you have to process to try to figure out what's going on here. There's a lot of occlusion in the environment and a lot of things that are distracting you, things like branches that have been baking in the sun that pop out in the thermal image. And those are all just distracting you from where the person really is, which is right here. So did anyone find that on their first try? I know somebody who's hiring imagery analysts. Yeah, I have a closer up version of this, but yeah, this person is really occluded. They're laying down, they're wearing a yellow reflective vest, and you still can't see them, right? That's kind of the point here. This is a very tough challenge. And now imagine trying to fly a UAV while you're doing that, right? So this is tough. And even if you did have, say, a machine learned model that maybe got you 99% reliable detection of humans from aerial perspective imagery, if you don't get these unoccluded views of the human on the ground, you still have a problem. And so we argue this is really what's limiting the state of autonomy as applied to the wilderness search and rescue application. What I mean by that is operators tend to fly these missions manually so that they can make ad hoc or in-flight adjustments of the position of the UAV to get better, less occluded viewing angles. So this is that perception-aware planning loop. You want to be responsive to that imagery analyst role when you're flying the UAV. Now, unfortunately, there are a bunch of existing coverage planners, but none of them really address these specific challenges and really handle occlusion well. What I'm showing you here is called Q Ground Control. It's a very popular ground control station software. And these are really easy setup, these surveys that give you some sense of complete coverage. You could use this, for instance, for creating an ortho mosaic of the ground. However, these aren't really designed to be very efficient. So what you'll notice here is that there's a lot of backtracking through the environment. If you look at the takeoff location in the kind of lower right corner up to the top corner where it starts its route. So that's not very efficient, which is critical when you're talking about these small backpackable UAVs. We're really talking about something on the order of 35 to 55 minutes of flight time per battery. And you're limited to how many batteries you can carry out into the wilderness. So we really want to try to maximize efficiency if we can. And then the bottom line is these don't really consider anything that's going on in the underlying terrain or the vegetation. So they're not occlusion aware. So when you search through the literature, you'll find there's one approach that helps us grapple with the problem of occlusion. What this approach consists of is breaking the problem into two subproblems. The first is called viewpoint generation. So that's where you ask the question, what camera positions do I need to achieve to call my coverage complete? And then there's this second problem of path planning, which is what order do I visit those camera locations in that maximizes, say, my battery life on my UAV or some other thing that I care about. And as it turns out, individually, this viewpoint generation problem and path planning problem are very complex, and so complex that people even write papers about how complex they are. So in different communities, these have an academic form. The first one there is called the art gallery problem. The second one there is called the traveling salesman problem. Okay, so for the uninitiated, the art gallery problem goes a little something like this. So say you're in charge of security at a museum and you have this weirdly shaped room like this, and your job is to place these security cameras down in a way where you can observe the entirety of the interior of the walls. but there's a problem. Each one of these cameras costs $6.4 billion of taxpayer money. So you have to basically find a minimal set or minimal configuration that'll do this task. And it turns out doing that is really complicated, and it's not something you can really brute force your way through for just an arbitrary polygon. So we have to rely on approximations for something like this. But then when you extend this problem to, say, the drones version of an art gallery problem, so in three-dimensional space, we lose some of those tools that we can use for approximation, so it becomes even harder. There was one algorithm we did find when we looked in this area of the literature that showed us some potential. And so we're going to leverage this algorithm called the Vantage Waypoint Set Generation algorithm. What they're doing here is these little shapes you see here in pink. They're modeling terrain, uneven, flat terrain versus, like misshapen or rough or non-flat terrain in the shapes you see there. And these green dots are a covering viewpoint set that are guaranteed to cover that entire area and all the faces of those shapes. So we're going to use a modified version of this later down the road, so keep that in your back pocket. Now let's assume we're going to talk about the path planning problem or traveling salesman problem. So now let's assume that you're the guy who has to go install all these cameras, and we've chosen these blue dots as where we want the cameras installed. And you want to complete this task as fast as possible. So travel the least amount of distance and find an efficient route to do it. This is another complex problem that if you try to brute force your way through it, even for this 7 vertex traveling salesman problem, you'd have to check 5,000 or more solutions and see which one gives you the minimum distance if you're going to do a brute force approach. So these don't scale well. So if you have a lot of vertices in your problem, you really have to rely on heuristic methods or approximations. As it turns out, for the type of traveling salesman problem we're going to use, which is a metric TSP, which all that really means, to summarize, is just moving from point A to B is the same as moving from point B to A. So they have the same cost there. For solving a metric TSP, these work actually really well in practice, surprisingly. What I'm showing you here is a version called simulated annealing. We're not going to use this version, but this is a clever way of doing it. It just takes a bit longer, but it's basically a local search that uses probabilistic techniques to jump out of local minima. We're going to use this one called the Lynn-Kernighan heuristic, which is often considered to be one of the more efficient and accurate approaches. And it's very capable. It can handle vertice sets as large as 10,000 in some cases. So it's considered one of the better ones out there. And we're just going to let this do some heavy lifting for us down the road. Okay, but before we go back to our problem of occlusion-aware coverage planning, we need to solve that viewpoint generation problem, which means we need to know something about the geometry of our environment. We really can't do that task without that. So what typically happens when you look at the literature is this explore then exploit strategy, where really the goal here is you need some sort of geometric proxy. This is something that tells you about the geometry of your environment that you can use to do these globally optimized viewpoint planning, and then you can go fly those views. The problem is that wilderness search and rescue is an emergency situation, so we don't have time for that. And so we need to basically come up with a geometric proxy using a priori information. And what we propose is that we can use just pre-existing LiDAR survey data. We think this is a good assumption that we can make because LiDAR survey coverage is actually getting quite complete, especially here in the United States and in other parts of the world. Governments have found tremendous utility in these surveys, and they serve a variety of different functions like forest monitoring and flood zone planning and things like that. And here you can see an example of this LiDAR survey point cloud, and it gives you a very clear picture of where the trees are and where they aren't. So with this, we should be able to derive a geometric proxy of our environment and plan some viewpoints that should be pretty effective at getting us the coverage we want. And so unlike that Vantage Waypoint Set Generation algorithm problem where they were modeling flat versus uneven terrain with these geometric shapes, we saw a different application where maybe we could model the trees in the environment using bounding boxes or other kind of fundamental shapes. And so that's where we're going. So we're going to use LiDAR point cloud data to derive a geometric proxy. The geometric proxy is going to represent the configuration and the extensive trees. And this actually is a problem, subproblem called the individual tree detection and segmentation problem. And as it turns out, it's not a fully solved problem, but there are a lot of methods and techniques out there that do a reasonably good job and will get us what we need for our missions. Okay, so at a high level, what we're proposing in this dissertation work is an occlusion-aware mission planner that starts with a LiDAR point cloud and ends with an executable mission. So a waypoint mission that you can load up into your ground control station and fly autonomously and be confident that you're getting the viewpoints you want. We do a lot of processing on this point cloud, and I'll explain these steps in more detail later. Really, the point again is to do that tree extraction, figure out where the trees are, come up with some geometric proxy. Once we have that, we turn this into a graph problem. And then we solve this graph problem using the tools given to us by the Vantage Waypoint Set Generation algorithm with some modification, though, to include very practical constraints. And then we use that TSP approximator to sequence these waypoints, and from there we convert that to a mission plan. So there's 3 key steps here. There's getting our geometric proxy. there's coming up with our viewpoints, and then there's sequencing the viewpoints. So when you put these 3 steps together, this is our algorithm called the Vantage Waypoint Set Generation Algorithm Plus, or VWSGA Plus, to differentiate it from the original VWSGA. So let's talk at a high level what these steps are doing. We'll start with the geometric proxy. This is our terrain model, right? So I showed you bounding boxes of trees, but we could use any polyhedron shape we want with one restriction. So we use these polyhedron of a special type that in plain English, what we're doing is we're taking the walls of these shapes and kind of slanting them inwards as you go up in elevation slightly. So there's a little bit of angle to them. We're going to exploit that fact later down the road. Other than that, there's no restrictions here. You can use any kind of polygon shapes you want. They can even be non-convex. And then the only other thing to care about here is you see this black boundary here. Not only do we care about covering the polyhedron with views, but we also want to cover all the points in between the black boundaries. So that's going to be a part of our definition of coverage. Okay, so what do I mean by coverage? Well, we're using a sensor model that's just a downward facing camera with a conic field of view. So it's completely parameterized by this alpha, the angle alpha here. And to check visibility, we just do 2 tests. We check if a vertex is visible from a vantage point, if it's within the field of view cone, and you can see these circles here kind of represent these level sets of that cone where we can just check if a vertex is in or out of that circle. And then we also, if we determine it is within the field of view cone, we do a second test where we just draw a straight line. We have to have direct line of sight. So we draw a straight line from the vantage point to the vertex and do intersection testing to see if we can draw a straight line or if it intersects a face of the polyhedron, in which case it wouldn't be visible. So once we have this geometric proxy, and then we know some mission parameters, so things like our X and Y bounds, our minimum maximum altitude, and our field of view of our sensor, we can start our Vantage Waypoint Set Generation Algorithm processing pipeline. First thing we do is we decompose this environment into a graph problem. I call this the art gallery problem graph, or AGP graph for short. And this is actually the most computationally expensive and time-consuming step in the entire process. And what we've done here, all that you really need to know is that we've kind of condensed the environment down into a 2D plane. We've done a triangulation and some additional processing to ensure that this geometric object is essentially a non-intersecting polygon that's been triangulated. And that becomes important. You'll see the reason why we do that in the very next step here. Okay, so we have this art gallery problem graph, and this triangulation step is helping us it's going to help us figure out what our altitudes need to be later down the road. It kind of defines these local neighborhoods of what vertices can see and what they can't see. So we're going to try to separate out these vertices into distinct sets. And we do this by solving the 3 coloring problem. Now, as it turns out, the 3 coloring problem, for those who don't know, is basically given a graph, can you paint the vertices 3 different colors such that no 2 vertices share the same color, no 2 neighbors that are connected together. And for an arbitrary graph, this is yet another very complicated problem that you can't brute force. And so, but all that processing we did in the previous step helps us actually just avoid this. We can guarantee such a 3 coloring exists, and then we can also apply the 3 coloring in a very efficient way with just one pass through the vertices. So now we have these 3 distinct sets, and you actually just pick whatever your favorite color is, and that you'll have the basis for a covering vantage point set. But we really generally want the minimal set. Remember how expensive those cameras were in the analogy. And so we're going to pick the color with the minimum number of elements, and then we're going to compute using the geometry and then some other parameters we care about, accounting for things like any deviation in the flat areas of the terrain and maybe a safety margin. Then we can compute altitudes of these vantage waypoint sets. And now we have a 3D set of viewpoints that is guaranteed mathematically to give us complete coverage, meaning it can see all the faces of these polyhedron, and it can also see all the points in the black boundary that are on the flat ground. Now, using the original Vantage Waypoint Set Generation algorithm, there was a problem that we noticed almost immediately, and that's given certain scene geometries, you can end up with very impractically high vantage point altitudes when you're doing this computation. And this is primarily driven from that triangulation step. So these long triangle legs are basically driving the altitude that we need for coverage upwards. And so thinking about this problem, we thought this would be, if we could apply an upper bound, it would make this algorithm really useful, because without this upper bound, there's all sorts of reasons why you need to have a limited altitude in a UAV mission. Not only does the FAA require that you stay below a certain altitude, so there's a regulatory reason. There's also operational reasons, like you might be sharing airspace with another UAV and want to deconflict an airspace. And there's also technical reasons. Maybe your UAV can't even fly as high as the Vantage Waypoint Set algorithm wants you to. So all sorts of reasons why we want to apply an upper bound here. And in the original algorithm, it was just assumed that whatever altitude they computed would be below some maximum that they call Z max. So when you think about this problem, if you have to start with a vantage points that is really high and you want to bring it down, what happens is you're going to lose visibility. So the visible area is shown in green here, and you see we're going to lose some of that, which means we need to move laterally in space to spawn another vantage point in order to recover that visibility and get that back. The question is, where do we place these new vantage points? And in many cases, you might actually have to spawn several vantage points. In which direction do you go? Now you have a big search problem. So the solution to this problem that we ended up on is called Steiner point augmentation. So what we're doing here is we're adding additional vertices to our polyhedron map in a way that limits the triangle lengths and therefore limits the maximum altitude that you can even compute with this algorithm. So these are the Steiner points here. You can just kind of see a side-by-side comparison. As it turns out, this could be a really effective way of doing business. And so like if you see the blue trace here as the original solution, it has vantage points that are upwards of 200 meters or more. We applied one additional Steiner point to this problem, and we're able to bring that altitude window down to within, below 120 meters. So that's the bottom solution. You see there's our version. Now, this is not a typical result. So adding just one Steiner point does not, in all cases, get you what you need here. So we had to come up with a more systematic way of doing this, and we ended up with a gridded type approach, where here you can see it side by side with the original versus ours. The vantage point solution, the original solution is upwards of 60 meters, and here we're able to bound it between 30 and 40 meters. One other note, so not only are we improving this algorithm by applying these bounds, but by applying these bounds, we're also improving the efficiency. And this will come out in the data later. The reason why it's more efficient to fly a route that's bounded in altitude is it actually costs you a lot of battery life in your UAV to fly from low to high. So getting to high altitude takes a lot of energy, and so you'll see the energy savings come out in the data later. Okay, so from there, we have this 3D viewpoint set that gives us some mathematical guaranteed coverage with respect to that geometric proxy. We're just going to let that Lynn Kernighan help us out here to find our waypoint sequence. So we're going to solve a 3D metric TSP problem. Right here, this red trace is showing you a 2D version, but we're actually solving the 3D Euclidean problem, and we end up with a sequenced version of these waypoints that becomes our waypoint mission. And that's we're minimizing the distance traveled in that problem. So another measure of efficiency. Okay, so I think we have a basic understanding of the algorithm, and for this dissertation work to understand the performance, we wanted to understand how well this does in terms of coverage, but we also wanted to understand flight characteristics, so things we care about in terms of flight efficiency, because if this gave us 100% coverage, but took us 5 batteries to execute, then that probably wouldn't be worth it. So here's the first simulation we ran was a Monte Carlo analysis. So here we're running several random trials and trying to statistically characterize the things we care about. We're going to use this library called Python Dynamics, which gives us this nice quad rotor simulation. So I'm showing you our solution, VWSGA on your left, and then the original on the right for the same map. So we did a random generated map and came up with these solutions based on that. So I'm not showing the map here, just the waypoint missions. For this simulation, we used a full stop at each waypoint. So the UAV is going to stop at each waypoint. That was just a design choice, and you'll see why that matters in a moment. There's going to be a side effect of that choice, but in general, we felt this was appropriate because we're trying to achieve each of these viewpoints, and we want to say something about the coverage there. So if you use a controller that just gets close to the waypoint and doesn't actually achieve that waypoint, then the coverage guarantee goes away. Okay, so our Monte Carlo trials consisted of generating these random maps. We used a fixed area. We generated a random number of polyhedrons, so we varied the density of the occlusion in the map. And then we varied the altitude window that was required. And then we also varied the field of view. So for each map, we generated 5 different algorithms, waypoints based on these 5 algorithms. These first 2 are lawnmower missions. The first one has a 30% overlapping field of view. The second one has a 70% overlapping field of view. We also did the original VWSGA, the blue dotted line there, which doesn't respect any altitude bounds. So it's just going to go as high as it wants to. And then we did a capped version of that where we just applied the ceiling. So whatever that Monte Carlo trials altitude window was, we restricted the altitudes to those bounds. And then we did our algorithm as well. So here you see a side-by-side comparison or an overlay of the capped version of the VWSGA and then the VWSGA plus overlaid, and they all fit within this 3D geofence, I'll call it. And for each of these simulations, we measured the distance traveled, the cumulative thrust that was commanded by the waypoint controller, and then the completion time to complete the mission. We also used an additional measure called energy. So that's just, I'm not going to go into it too deep, but we used an energy model, an energy consumption model based on empirical studies that accounts for things like flying horizontally, hovering, flying upwards, or flying downwards. So you get a penalty for instance, climbing an altitude for a long time, right? So that'll help us kind of differentiate the altitude penalty. Here's the cumulative distance thrust, or this is basically the commanded thrust from that simulation. And you'll notice these spikes. What these spikes correspond to are when we have to stop at each waypoint. So decelerating and accelerating again will create this behavior. And what that means is we're going to incur a small bias against our algorithm in this analysis because we have many more waypoints because we are literally adding more waypoints through Steiner point augmentation. So more waypoints is more spikes. We're going to pay this tax more often. This isn't going to be a dominant bias, but you'll see it show up in the data table later. And then for coverage performance, we measure the coverage with respect to all the faces that were possible to see in the map, as well as all the vertices on the boundary. So both of those are accounted for in this coverage metric. Okay, so I'm going to show you what the data show for the simulated performance analysis. This is a little bit of a non-standard representation, so I'll just go over this key really quickly for if you haven't seen something like this, but this is a bar chart overlaid with a box and whisker plot. And so the reason I chose this is because I'm very vain and I wanted my algorithm to stand tall with respect to the other ones. So what you'll see here, for those of you playing at home, just the diamond, the yellow diamond is the mean or average. And then the box and whisker plot gives you a sense of the quartiles and the min and max. And then you have these black diamonds are the outliers. So what I'm not showing you is like standard deviations. That's not shown here. So the coverage percentage is on the y-axis. And then I'm showing you a gradient of altitude window from 5 to 30 meters in 5-meter increments. So going from light to dark is a widening altitude window. Okay, the keys down here if you need it. The results really quickly. The lawnmower with the 30% overlap is not worth talking about. The lawnmower with the 70% overlap got about 45% average, so less than 50%. And you can kind of see the range there in the data and how variable it was. The VWSGA capped version got about 87%. You can see this drastic drop off as the altitude window gets tighter, which is to be expected. And then ours came in first place here with statistically perfect coverage. I literally can't improve on this result. So, okay, so now the coverage is the most important metric. It's the thing we care about the most, but as I mentioned before, we also care about flight characteristics. So here's a table that shows those side by side. We have distance, time, energy, and thrust along with coverage. Here's the 5 algorithms we flew. You'll notice we've partitioned this table. The reason we did that is we're actually not going to really consider these top 2. The VWSGA original version doesn't respect any altitude bounds, so it's not playing the same game we are, so to speak. The Lawnmower 30 does, but we felt like it would be misleading to include it because it would just dominate all the categories, but only achieve 22% coverage. So it would be misleading to include it there. You would just see bold all across that row. So this is really the competition here between the Lawnmower 70, VWSGA capped, and VWSGA plus. We talked about coverage performance. In terms of distance time, VWSGA capped came ahead, but what we can say is we are on par with what you would expect for the 70% overlapping lawnmower pattern within the statistical margins, albeit at a higher variance, and I'll explain where that variance comes from shortly. The Lawnmower 70 used the least amount of energy, which is to be expected. It stayed at the same altitude, so it wasn't paying those altitude penalties. And the thrust measure, again, the VWSGA capped, had less stop and go. It used the least amount of waypoints, which is why it came in first place there. But again, we're on the same order of magnitude as the Lawn 70. But you'll notice here, that especially with the thrust measure, there's very high variance, almost more than twice the amount of the lawnmower. The reason for this variance is really explained by the fact that we are adding more waypoints, so we're paying that penalty again, right? What that also does for the other variance that you see in distance and time associated with the Vantage waypoints at Generation Plus, it means that we're solving a larger traveling salesman problem, which means we'll be more likely to get stuck in a local minima, so maybe have less optimal distance and also take longer to complete, so to speak. Now, we're going to show in the real data. So in the real world data, we actually flew these 2 algorithms, our version, and then the original VWSG plus, so not the capped version. So just take note here of what happens in the energy column and how much more efficient it is to bound your solution by altitude compared to the original Vantage waypoint set generation. So that's beyond the plus or minus standard deviation there. Okay, so once we had this performance analysis under our belts, we felt the next step was let's start our pipeline that goes from a point cloud to an actual flyable mission. So we developed this simulation with PX4, which is an autopilot firmware that we're going to be flying in real life. So that's in the loop here. We're going to start with a simulated point cloud, turn that into a mission, upload that to Q ground control. So this is the same ground control station that we're going to use for our real world experience. And Q ground control is going to talk to PX4 to fly this quad rotor, and that's going to be rendered in a simulation engine called AirSim. And if we did this right, then we could just literally replace the point cloud and quad rotor in AirSim with a real quad rotor and a real LiDAR survey. So here's an example of that whole pipeline working well. This is a very, this environment is called the blocks environment in AirSim. So it has just kind of these simple blocky shapes, but you'll see the quad rotor here. It's gonna try to follow these waypoints that we generated from our point cloud. It's not gonna use that same stop and go controller. It's just gonna try to get close to the waypoints. That's just the default controller in AirSim, but you get the gist here. The real important point is that Q ground control that you see in the lower right, is talking to PX4 and executing this mission autonomously, which is what we wanted to see. From there, we felt like we had enough confidence to move to a real world flight test. And so we chose to do some outdoor flight testings with a simulated wilderness search and rescue scenario. We went out to North Bend in Washington State here at Meadowbrook Farm, which you can kind of see. This is a LiDAR point cloud data we used for that. We used some methods that I described in my dissertation that are raster based to come up with our bounding boxes for our trees from this point cloud data. And so this is how we derived our geometric proxy. And with that geometric proxy, we computed different waypoint missions for the original Vantage waypoint set generation algorithm and then our algorithm. We flew these two different hardware platforms. And for all the flights, we measured things like distance traveled, the amount of time it took to complete the mission, the average speed and battery that you used during the mission. For sensor characteristics, just take note that there's two fields of view. 85-degree field of view corresponds to a very high resolution visual sensor. 46-degree field of view corresponds to a thermal sensor at a much lower resolution. So those are the two distinct mission sets, 46-degree or thermal and visual at 85-degree. And for each of those, we did 3 missions or 3 waypoint missions, a lawnmower, also with the 70% overlap, just like we did in the simulation, the original Vantage waypoint set generation algorithm, and then the plus. The original Vantage waypoint set generation algorithm that we flew is, it's not the capped version that I showed you in Monte Carlo sim, but we did actually have to cap some of the waypoints because otherwise we would be violating the FAA's regulations. So about a handful, about 6 of the waypoints were adjusted by maybe no more than 5 meters down in altitude to comply with the law. For the wilderness search and rescue scenario, we hid people and objects in the forest. These people were placed without knowledge of what the flight paths would be. In fact, we didn't even know what areas were really accessible when we got out here. So we just kind of played it by ear, placed these people, but we did try to deliberately place some people in more occlusion and less occlusion. So we had some sort of distinct like easy, middle, and hard class of objects. Person A here in particular, that's the person we were looking for at the start of the show. So that's a teenage boy laying on a blanket there, wearing a reflector vest, and you can see his viewpoint looking straight up into the sky right next to him and see how occluded that is. There's a very small window in the sky that you need to achieve to be able to see this person. Here are the trajectories we flew, all stacked upon one another, and you can really see the altitude difference there. The red is the original Vantage waypoint set generation algorithm, and then our version is the yellowish orange trace, and then blue is the lawnmower. So what does the data show us? Well, our algorithm flew these missions faster and used less battery in general, in all cases, really. And that distinction is really, really prominent in the 46-degree or the thermal missions. In particular, we used 42% battery. The next best was 48 and 66. The average speed, we measured average speed, but it turned out not to be really relevant. So the lawnmower has an average speed because it has these long straight legs and it's just able to stay at a higher average speed, but that didn't really matter. It took 17 minutes and some change to finish the 46-degree field of view mission, whereas ours took just shy of 11 minutes. So we wanted to say something about the coverage performance of our algorithms in these real world tests, but we can't do that same thing we did before with ray tracing and brute force casting. This is a real world environment. So what we decided to do here was do a manual video analysis. So we looked at all the videos, we tried to identify the objects in all these videos, and then we drew bounding boxes around them. We used the size of the bounding box to determine whether these targets were detectable, recognizable, or identifiable according to a pretty well-established standard called Mesnick standard. So by detectable, I mean, you're able to say there is an object there. By recognizable, you're able to say that object is a human, and by identifiable, you're able to say that is a woman wearing a blue hat. So it's about the level of detail and features you can see with these different viewpoints. And so across the board, we didn't miss any targets with any of the missions. The lawnmower actually got kind of lucky in one case. It should have missed a target, but there's this kind of arbitrary choice of transect angle that it just happened to fly right over that most occluded position. But in general, no targets were missed. So they were all detectable, and the VWSGA Plus did just marginally better. So it detected all the targets. It got it achieved recognizable status on 3 of the targets and identifiable status on 2. The next best was 1, 2, and 2. Here's an example of just using a computer vision model. This video is broken. Oof. You can see it there. Okay, yeah. So like using a computer vision model on one of our Vantage waypoints at Generation Plus routes here. So you can see if you had some sort of automated detection here, we would be achieving viewpoints that would be amenable to that kind of approach as well. Okay, so what can we conclude? So the very first conclusion is we do offer a coverage guarantee with this algorithm, but terms and conditions may apply. So that means this coverage guarantee only extends to that geometric proxy from which it was derived. So any mismatch between that LiDAR point cloud and reality, or any mismatch or inaccuracies in your ability to extract the tree locations are going to propagate and cause you less good coverage. So here we see some areas for future work. You really want some sort of online element. That LiDAR point cloud data I mentioned, by the way, was from 2017, so it's very old, but it ages really well in general because tree growth is such that it doesn't really change your occlusion picture, and the configuration, the trees don't really move in the XY plane a whole lot, right? So, but there will be mismatches and things can happen, new structures can be built, trees can fall over. So you want something to deal with this model mismatch and some online component of this. So we're thinking about ways to include like a replanning element. And there are computer vision techniques that can detect in real time 3D bounding boxes of certain things. So I've seen one for like cars, for instance. That's a much harder problem when we're talking about trees in a wilderness environment, but something like that could be down the road and forthcoming, and you could use something like that to plan off of. I also talked in my dissertation about a graph neural network-based approach to do the viewpoint generation problem, but essentially solving the 3D art gallery problem with graph neural networks. This is kind of a novel aspect because graph neural networks are used in all sorts of other combinatorial optimization problems, but they haven't really been applied to the art gallery problem. And so we saw an avenue here to really get to a full 3D approximation of an art gallery problem using graph neural networks that I have the beginnings for in the appendices of my dissertation. The next big takeaway is that, so this isn't really a fully automatic pipeline. You can't just start with a point cloud and get a mission instantly. You have to do some work to get that tree detection to be fairly accurate and to the point where you're not clustering trees together, because you really want those individual trees to be separated a bit. Also, this is just a single agent traveling salesman problem we're solving here. So some extensions for future work here there are some point cloud-based methods. So we use a raster-based method for our tree detection, but point cloud-based methods seem to be more automated or less sensitive to parameterization. So those should be investigated to see if we can get to a fully automatic pipeline. And then there's an extension to some work done out of Stanford called Waddle. It's a large area coverage planner that solves the coverage problem for multiple agents. So this is called the vehicle routing problem. It's like a multi-agent traveling salesman problem. And that would be a really cool extension to see this occlusion-aware coverage coupled with this planner, because it would allow you to incorporate things like flight constraints on your battery, as well as your flight times and speeds as well. So you can incorporate a bunch of more constraints into the problem as well, and come up with multiple paths over a large area that you can fly with either multiple UAVs or all with the same UAVs in sequence. And then lastly, so yeah, I mentioned that we are doing the Steiner point augmentation, and as it turns out, there's in very tightly constrained sets. So if you have a very tight altitude window and a very tight small field of view, that's going to drive the number of waypoints you need for the Vantage waypoint set Generation Plus pretty up, and there's an exponential relationship there. And so there are going to be cases where this may not be suitable for your mission set. So if you really can't widen your altitude window or use a sensor with a wider field of view, then this will need to be addressed with future work. And we're thinking about ways here to do that Steiner point augmentation mo better, as we say. So just trying to find smarter ways to place those and maybe do some consolidation, remove a little bit of redundancy there. Now, whether you love or hate this research, I hope this next slide will provide some context. So Eurus alluded to this. This is my transcript from my very first go at college. After 2 semesters, I was not doing well. And I just want to talk to the professors who gave me these Fs. And I just want to say, how you doing? How you doing? Okay. Okay, so with that, I just want to first thank my committee. I mean, this committee has been just outstanding with their support and their ideas and their mentorship. It's just been wonderful. I even have so David Sheen here is our graduate school representative. His job is really just to make sure we're following the process, but he couldn't help himself. He just had great ideas and was really interested in this research. So we actually used a lot of his feedback as well. So if I could give out a bonus point, I think I would give it to you. All right. I want to thank the Snohomish County STAR and Seattle Mountain Rescue folks and Chelan County and Lake Wenatchee, who helped shape this research and help us get kind of a picture of what these operations are like and where the pain points are. And there's too many people to name here and a lot that I really couldn't fit onto this slide, but I would not be here today without the love and support of my friends and the help from my colleagues. And these people all have stock in my PhD status. So thank you all from the bottom of my heart and for my family who's here and have been supporting me all the way. So with that, I will go back to this slide and leave it open for questions.